Hey, fellow mathematicians! Before we get into the episode, we want to let you know some important information about Math is Figureoutable merch.
Yeah, we know so many of you love all the great designs that we have on the Math is Figureoutable website, and you might want to share the love with some fellow mathy friends.
If you're in the US and order apparel like t-shirts and hoodies by December 10th, it will arrive before the holidays. If you're out of the States, you'll want to order sooner than that to make sure you get your merch. Make sure you are holiday ready and get your order placed by December 10th. Now, on to the show. Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that algorithms are amazing historic achievements, but they are not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
And we invite you to join us to make math more figure-outable.
Hey there, speaking of grappling with mathematical relationships, I pulled a paper that I had from last week just to take notes on. I knew we were doing string today. And I have two things circled on my paper that when we did the last problem, which was 2 to the 4th times 2 squared, I called it 2 to the 6th. And kind of at the end, you said, and I'm going to also pull out that that's 4 to the 3rd.
Okay.
For whatever reason, I circled those equivalencies, and
the 2 to the 6th and the 4 to the 3rd.
Yeah, and I've been tinkering with it a little bit because at first I thought like there's this nice double the base half the exponent, and I was just trying to figure out.
Wait, what?
So
double the base, half the exponent.
Yeah, that was true there, but I mean, honestly, I'm not sure if that's always true. I just have been tinkering for a second while I'm waiting for you. And at first I thought, well, maybe the base and the exponent has to be even, but then 3 to the 4th is equivalent to 6 squared. So in that case, the base is odd. So anyway.
But 3 squared is not equivalent to 6 to the 1st. Is that the pattern? Double the base, half the exponent?
I'm wondering when that would be true.
Oh, okay.
I don't think
so
it's
you're not suggesting it's always true.
No. I'm just wondering, like,
because I just found a non-example.
Yeah, I'm wondering, like, when is it just a fluke that was true, or is there some sort of
okay? Subset? I have an idea, but will you let me think about it?
Yeah.
Okay.
All right, on to today. Sorry to derail us already.
So this is fun because this is one of the things that we do, right? Is that I will come at a lot of things from kind of a traditional background of having taught higher math, and then you'll come in and go, well, what about this? And I'll be like, I've never thought about that. let's think about that together.
Oh, so and I just realized what I wrote and said, and they're not equivalent.
Which ones?
3 to the 4th and 6 squared.
3 to the 4th. And and I wasn't listening because I was doing my own thing.
I know.
No, those are not equivalent. Not even close. Which is super interesting, right? Because like 3 to the 4th, you might look at that and go, well, 3, that's so small. Raised to the 4th, that's not going to be very big. 6, that's a really big number. So you square it. No, like 3 to the 4th is much bigger than 6 squared. Like tons. But anyway, okay. So funny story that kind of follows along with what we were just talking about. I was doing some filming for some wonderful work that we were doing, and we were in a wonderful teacher's classroom. Abby Sanchez has been an amazing thought partner over time. Really have enjoyed working with her. Several years ago, we were doing some filming, and in the middle of a problem string, Kim looked at me and she just kind of shook her head. And I was like, what? So Kim was there as kind of a pedagogy check. Because at that point, you had done less higher math. Your kids were not even old enough that you hadn't done higher math, and you hadn't really done since high school. So you weren't really there for the math. You were there for the pedagogy. And you kind of just shook your head, and I was like, what? So Abby got done doing that particular problem string that I had written, and you handed me a little piece of paper. I think it was a Post-it note. And you were like, this would be a better string. I mean, I think you said it maybe more judiciously than that.
Really? Really, did I?
Your point was like, here's a better, and I was like, what? And she goes, you said something like, like the way you're doing it is fine, but this would get at those relationships a little bit better. And for those of you that have followed our work over time, if you've taken one of our Building Powerful Mathematics workshops, gotten any of our free downloads, you'll notice that we now give you what we affectionately call the half sheet. And that half sheet is a problem string on the left. Well, so it's split into two. And on the top, there's a problem string on the left. And next to it are kind of some hints or some things to think about, some important things not to forget while you're doing each of those problems. And then on the bottom is what your board could look like when you've finished the problem string. Well, that day was the birth of those half sheets, which for a while we called them Kim's notes, because Kim, you handed me that little sheet of paper, and on it, it had the problems on the left, and then it had little things that you would think about, not to forget, and ways to say and things to emphasize to the right of each of those problems. And we talked about it with Abby. And then in the next class period, she did it your way, was much better, went much better. And the reason I'm telling that story today is it was actually this problem string is the one that you rewrote. So you haven't looked at it for years.
I don't remember. I remember that happening. I remember Kim's notes. I don't remember what string it was at all.
All right. So I'm just going to throw this string at you.
Okay.
We're going to do it together.
Hopefully I can do it.
So listeners, if you've been listening the last couple episodes, we threw out that it could be possible that we could do a sequence of tasks that could help kids really reason exponentially. Exponents are multiplicative at their heart. So this is multiplicative reasoning, and we're heading towards exponential functional reasoning, which would be in the functional reasoning, but we got to reason exponentially first. Well, I say first, it's included in, it's within. And so what's a series of sequence of tasks? So we did one 2 weeks ago. We did one last week. Let's do another one that could continue to get kids reasoning exponentially. I think you could do this particular string in 8th grade. I think it would be totally appropriate in an 8th grade class. Maybe a little bit earlier, but I think for most people's standards, it would appear in about 8th grade. Okay. So first problem. What is 5 cubed? 5 raised to the third power. While you're thinking, I'm going to take a drink.
Okay. I'm going to call that 5 times 5 times 5, which is 125.
And how do you know that 5 times 5 times 5 is 125?
Because 5 times 5 is 25, and 25 times 5 is 125.
Okay, so this is what I have written on the board right now. I have 5 raised to the third power equals 5 times 5 times 5, which is what you said, equals 25 times 5 equals 125. Does that track? Yep. Cool. Next problem. What is 5 squared times 5?
Also 125.
And we wouldn't spend a lot of time here, but I would ask kids, and a lot of kids would say, Pam, it's just 25 times 5. We did that above. That's 125. And so now I've written 5 squared times 5 equals 25 times 5 equals 125. And then I might say, you're saying that we had just done 25 times 5 above. And so you know that that's 125. Well, what did we also say in the first problem? 5 cubed. So now I've got on the board 5 squared times 5 equals, and then a few things, but also equals 5 to the third power. Cool. I might throw above that 5 squared times 5, that I might throw a 1 above there just to like, okay, so like 5 squared times 5 to the first power is 5 to the third power. Cool. Next problem. How about 5 squared times 5 squared? What do you got for that one?
That is 25 times 25.
So I've written that down, 25 times 25.
Do I know that? I know 5 cubed, which is 125, times 5 is 625.
So I wrote down 25 times 25 equals 5 cubed times 5 equals 125 times 5. And then you know that's 625?
Yeah.
And does that feel like 25 squared?
I thought 25 squared was 625, but I don't have them all memorized, so.
But you just kind of played it out. You're just like,
yeah,
sure enough. Sure enough, indeed it is. Cool.
Yep.
All right. The last thing that I might write down is how many 5s did you just multiply?
4 of them.
So then I'm going to write equals 5 to the 4th. And then I might back up and say, so 5 squared times 5 to the 1st was 5 cubed, and 5 squared times 5 squared is 5 to the 4th. So if I'm multiplying the number of 5s, I can put that as the little exponent, and I could say the base is 5 and the exponent is 4. That means I'm multiplying 4 5s together. Okay, cool. Next, actually, before I'm done with that problem, I might say something like, it looks like in 5 squared times 5 to the 1st, we could write that 5 cubed as 5 to the 2 plus 1. Mm-hmm. And in the 5 squared times 5 squared equals 5 to the 4th, we could write that as 5 to the 2 plus 2. Cool. Next problem. How about if the next one is 2 cubed times 3 squared? 2 cubed times 3 squared.
2 cubed is 2 times 2 times 2, which is 8.
Okay.
And 3 squared is 3 times 3, which is 9. So 8 times 9 is 72.
So I've just written on my paper 2 cubed times 3 squared equals 8 times 9 equals 72. I'm asking myself if I should have written out the 2 times 2 times 2 times 3 times 3, but I think I might not yet, even though you clearly said it. I think I might not yet, because I think I might say, based on what we kind of did above, where we had 5 to the 4th equals 5 to the 2 plus 2, and 5 cubed equals 5 to the 2 plus 1, can we write 2 cubed times 3 squared as 6 to the 5th? And I put a question mark above that. So I wrote equals question mark 6 to the 5th. Because above we just said we could add stuff. And so can we add that 2 and 3, those two bases, and that 3 and the 2 exponents? Can we add those? Because you just said, we kind of said above that maybe we could add them. So I wonder if we could add them here. And is 2 cubed times 3 squared 6 to the 5th?
It is not. Do you want more than that?
Yeah, maybe.
Because when you're adding the exponents, you're saying you have that many of the base, but you change the base. When you multiply 2 times 3, you change what the base was.
So this might be the moment where I would have somebody say, yeah, 2 cubed is 2 times 2 times 2, and 3 squared is 3 times 3. So if I'm looking at that 2 times 2 times 2 times 3 times 3, there is a 6 there, but there's not 5 of them, right? Mm-hmm. Like 6 to the 5th, no. So then I would say not equivalent to 6 to the 5th, not even close. Mm-hmm. Is that okay?
Yep.
All right, cool. Next problem. How about 2 squared times 3, sorry, 2, I said 2 squared, I wrote 2 cubed. 2 squared times 3 squared. Okay, so now the exponents are the same. So maybe that means we can do something cool now.
2 squared times what? 3 squared?
Mm-hmm.
2 squared is 4, and 3 squared is 9. So 4 times 9 is 36.
Okay, and then I might ask everybody, is everybody clear on that? We're all good. Cool. I wonder before we said that you had to have something the same. So I wonder if this time we could say, is that equivalent to 6 to the 4th? Like maybe now we can add stuff.
Also no, because the bases, you change the base again. So
it's not the exponents that have to be the same.
You still have 4 of something, but it's different somethings.
So like if we wrote it out, what it means, it'd be like 2 times 2 times 3 times 3. Mm-hmm. And we don't have a base of 6.
Right.
So not equal to 6 to the 4th. All right. Rude. Okay. Next problem. Kim, how about 2 squared times 2 cubed? 2 squared times 2 to the 3rd power.
That is 4 times 8, which is 32.
Okay. Is that equal to something?
Mm-hmm. That is the same as 2 to the 5th.
How do you know?
Because I have 2 2's multiplied and 3 2's multiplied, and that's 5 2's.
So I wrote underneath. So sorry, blah, blah, blah. 2 cubed times 2. Sorry. Wow. 2 squared times 2 cubed equals 4 times 8 is what you said. Underneath the 4, I wrote 2 times 2. And underneath the 8, I wrote 2 times 2 times 2. There's your 5 2's. And class, how have we said we're going to write 5 2's? That's 2 raised to the 5th. Nice. Okay. Could we also write that as 2 raised to the 2 plus 3? So when can we sort of add exponents? Because it looks like we just came up with some things that we could do and couldn't do. When can we add exponents?
Only when the bases are the same.
And how do you know? Like, is that a rule you've memorized?
No, because when the bases aren't the same, like in the previous 2 problems, if we multiplied them together, then we got a different base. Here, we're just saying we have 2 2's and 3 more 2's multiplied. It's the same thing. Just it kind of reminds me of like at a younger grade, like repeated addition can become multiplication, but only if you're adding the same number over and over.
Oh, that's very nice. Yeah. So if you're adding the same number over and over, you can write that as multiplication. If you're multiplying the same number over and over, you can write that as an exponent or exponentiation. Nice generalization. Cool. So next problem. What if I said 2 raised to some number A times 2 raised to some number B? Could we write that in an equivalent expression?
That would be x to the A plus B.
So 2 raised to the A, 2 raised to the B.
Sorry, did you say x?
I said 2. Yeah, you just go really general on me.
2 to the A plus B.
And what does 2 to the A plus B mean?
It means 2 A2's and B2's. The A number of 2's multiplied and the B number of 2's. That's how many 2's we're multiplying.
We're multiplying a ton of 2's, and we first multiplied A of them, and we multiplied B of them, and we're multiplying them all together. 2 raised to the A plus B. Nice. So I might write that as 2 times 2 times 2, and then with how do I say this? With like a bracket underneath, a brace underneath it. So it's like I'm encompassing 2 times 2 times 2. Oh, let me say that better. 2 times 2 times 2 ... times 2. So like, and then I put the brace underneath it to say that's A of them, A of those 2's, times, and then some more 2's times each other, ... times 2, and a brace underneath those to say there's B of those. So how many total 2's are multiplying together? A plus B. That's how many I have multiplying together. Be a way of doing that. Cool. And then I might say, so what if I had, now I'm going to get even more general, x raised to the A times x raised to the B.
Here we go. X to the A plus B.
X to the A plus B, because we've got A x's times B x's. We got a whole bunch of x's times each other. How many times each other? A plus
B.
Yeah, nice. Cool. How would that help you think about something like 3 A to the 4th B? So 3 times A to the 4th times B, all times 5 A squared B cubed.
So I have 4 A's and 2 more A's.
Multiplied together?
Multiplied together. So I put A to the 6th.
Okay.
And I have B times B to the 3rd. So I have B to the 4th.
Okay.
And then 3 times 5 is 15. So I have 15 times A to the 15, A to the 6th, B to the 4th.
And how did you know B times B cubed was B to the 4th?
Because I have 4 B's being multiplied together.
It's all being multiplied together. So one way that I might do this with students is, well, first of all, I'd throw it out and let them do what they do. But I'm going to have some students that are going to be like, what? I don't even know what's happening. We could have somebody share that in that 3A to the 4th B, you got a bunch of stuff multiplied together, and we could write it all out. We've got 3A times A times A times A times B, and we're going to multiply that by 5 a squared b cubed. So I could write that as 5a times a times b times b times b. Now, I don't want to do this too many times, but what I want to engender in kids' heads is that when they see b cubed, they're thinking b times b times b.
Right.
Like they're like, okay, that's b. I've got 3 b's multiplied together. And when we've got multiplication, we can use the commutative property. Then we could do kind of what Kim just did, and we can move things around and put all the numbers together and multiply them. The 3 times 5. We can put all the a's together. How many a's did we have multiplying together? 6. A to the 6th. And then put all the b's together. How many b's did we have? And with that sense of what's actually happening, bam, we have kids that are clearly adding exponents, but they're doing it because they are reasoning about what's happening. Because math is reason-aboutable. All right, Kim, do you think it's possible that we could do a sequence of tasks like we've done? And now somebody's going to say, Pam, that took you 3 tasks to get kids to one of the exponent rules. And I'm going to say, no, it took me 3 tasks to get kids to reason about exponentiation, to reason, to like own what's happening. And I'm going to suggest that maybe not every kid in the room owns it yet, but I'm doing enough things to keep kids challenged. Now you're like, how are you keeping kids challenged? Well, you heard Kim start today's podcast thinking about some generalizations because we're actually understanding what's happening. Yeah. Kids like Kim are off thinking about generalizations while they're getting good practice. Notice I'm giving kids problems. They're getting instant feedback on how they're thinking about these exponent problems. We're getting quite a bit of practice done in just a few minutes. And we're building understanding not only for quote unquote exponent rules, which I'm going to call exponent relationships, but towards exponential functions. Like we are building exponential growth. We're feeling that it's multiplication is happening here. It's not what a lot of kids, I think, come out of when we give a couple of rules is they're like, oh, okay, so for exponents, you add, you subtract, and it doesn't make any sense, but you just like, okay, got it. Like these weird rules, and I don't know which ones to do, but I'll just memorize. Or we can actually build all this groundwork that really is going to come out and pay dividends now because they actually understand what's going on. They're confident in what they're doing, and later when we need to build on it. Yeah. Yeah? All right, I got a couple more for you, Kim.
Okay, can't wait.
We'll do a couple more in the next couple episodes.
Sounds great.
Y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com and keep spreading the word that math is figureoutable.
Hey listeners, don't forget, if you love Math is Figureoutable merch and want to share the love with your family and friends, now is the time.
That's right. If you're in the U.S. and order your favorite t-shirts and hoodies by December 10th, it will arrive before the holidays. Share the Math is Figureoutable love with your favorite people and keep spreading the word that math is figureoutable.